Okay, so we have been looking so far at the last class at least, we have looked at some acceleration techniques, we have looked at preconditioning the unsteady term for 1D Euler equations. Okay. There are some more acceleration techniques that we need to look at, some of them are relatively straightforward ideas that come from things that we have seen so far, ideas that we have discussed so far. Okay, so I will just use that. I will just use that to introduce at least two other techniques. Fine, and maybe I will suggest a problem that you can try out for yourself for one-dimensional flow. Maybe write out the quasi 1D equations. Right, I will just write it out. I am not going to derive them. You can derive them. You have already seen them derived in gas dynamics, but still you can derive them. And then if time permits, we will get into a larger class of, right, a larger algorithm which will take me multiple classes to, at least 2 classes if not 3 classes, right, to talk about acceleration schemes of another nature. Okay, fine. Okay, so first let us look at, we will just go back, look, I will write the equation in delta form. I will write the equation in delta form simply because as always I forget the delta t there. I write the equation in delta form simply because I know that if this term were not there, it would become the explicit scheme. Okay, so I write the equation in delta form, and I am going to use this to just point out 2 ways by which we can accelerate convergence. Okay, and the reason why I am talking about this is I want you to get a flavor of the kinds of things that you should look for when you are writing your code. Right, you say yes, last class I said I want the wall clock time, the time that it takes for the answer to come back, to be as quick as possible, as short as possible, the duration to be as short as possible. So towards that there may be effort that you make, various kinds of things that you do. When I write this delta form simply because we use this argument saying that when I get to the solution R, the residue will be 0. Okay, so I will repeat that argument. So as a consequence, as long as this is not singular, delta q will be 0. Okay, and therefore it really does not matter when I get to convergence. If I am interested only in the steady state, you are no longer talking about the transient. If I am interested only in the steady state, then I can pick this matrix in some form so that it is easy to compute. Is that fine? Right, and we have used this argument before. We came up with the LU approximate factorization. There are other schemes that we have talked about, where you can actually replace this by something that is going to get you to the solution faster. Let me just put it that way. Okay, is that fine? Now if R goes to 0, delta t times R is 0. Okay, so one obvious thing that you can do, right, and think back to the demo. What did I do in the demo? In the demo I set delta t by, I picked delta t by delta x. I didn't pick the CFL. My delta x is not changing, therefore my delta t is not changing. Okay, already when I do this, you know that if my delta x, the intervals were not equal in size, you already know that the delta t will also change from point to point. But I have picked a fixed delta t, I didn't pick a CFL. But you could pick a CFL. You could pick a sigma value, okay, you could pick a sigma value, so that it will turn out that the delta t is not same from point to point. In fact, you can ask yourself the question, so this is at some point, this is of course a system of equations, but at some point, for any point, if you were to take a delta t, right, so if you had, let us just pick a bunch of grid points here. So you could pick a delta t here which is different from the delta t at the adjacent. So you could have a delta t p and a delta t p plus 1. Is that fine? So the time can be changing from point to point. This is called local time stepping. So what could be the potential issues? What could be the potential problems? Well, we do not know if it will converge to the right solution. right. Again I would expect that anybody who studied mathematics, uniform convergence and all of that, we have a problem. We already know that we don't have uniform convergence, and we are starting to do funny things like this. We are saying, well, if there is a spot where the solution converges very quickly to a solution, steady state solution, let it go. Why should it be held up by something that is going at a small rate? Am I making sense? Anywhere where I can take large time steps, let me take large time steps. Where I am constrained to take small time steps, I will take small time steps at those points. Is that fine? So basically what we are doing is, by doing local time stepping, we are saying geographically, point to point in the domain, my solution is, so it is no longer, if I say first time solution at first time step, solution at second time step, solution at third time step, they are not really a solution. It's not, I mean, I can't even imagine it as a candidate solution. It's basically, well, some state vector q at the first time step, whatever that means, right? But I say first time step, I don't say at delta t. My language is already changed. I say first time step, I don't say at delta t. It's not at delta t, 2 delta t, 3 delta t, because I am not anyway bothered in the transient. So I don't care. And if it gets to a steady state solution that I want faster, my experience has been that you do get to the steady state solution faster. So if I am looking for the steady state solution, I am likely to do local time stepping, right? In my experience, you do get there faster, so I am going to do local time stepping. Am I making sense? Okay. So this is one possibility. So what I did in the demo, now see, once you introduce language, we have to make sure that the vocabulary is complete. So if this is local time stepping, what I did in the demo is called global time stepping, right, just as a contrast. So global time stepping. You have to be careful, because if you switch from one to the other, or you are making a presentation where both are there, you have to have clarity. This is local time stepping, this is global time stepping, right? Okay, is that fine? And obviously there are things that you can do in between. There can be places where you say get to the steady states quickly, there may be places where you are interested in transient, I don't know, right? There could be combinations that you could use. There could be a strip where you use global time stepping and a strip where you use local time stepping. There are all sorts of possibilities. Is that fine? Okay, that is one possibility. The other thing, remember, I want to get only two, I only want to get to the steady state solution. So we talked about fancy things that we could do to this, we approximate factorization and so on, but there are simpler things that you can do. Okay, how many terms does the flux Jacobian have? Flux Jacobian is A. It's a 3 by 3 matrix. You can imagine if the problem was in 3 dimensions, if you are solving the 3-dimensional Euler equations, it's a 5 by 5 system. The expressions aren't, I mean, they are okay, but they are not that great, right? They are pretty expensive to calculate. So then I ask the question, do I need to calculate it at every time step? I only care for the steady state. Do I really have to recalculate this A at every time step? Would it really hurt if I kept it constant for a few time steps? Am I making sense? Okay, so I can take the attitude, I am only looking for the steady state. It is pretty close to the original system. I will just keep A constant. And this can clearly be done. This can be clearly done whether you are doing LU approximate factorization, whether you are doing local time stepping, they can all be done together. It is not that it is one or the other. So one of the things that you can do, of course, remember that the first 3 elements are 0, 1, 0. I mean, that does not cost you anything, right? It's only, right. So I am not saying it's 9, but still, in the case of a 3-dimensional flow, I am to make the sale, right? I am telling you that I am pushing the 3-dimensional flow. You will have 3 flux Jacobians. Each of them are 5 by 5 matrices. At every time step, at every grid point, you have to calculate 25 into 3, right, 75 minimum. Am I making sense? So the question is, do I need to do it at every time step? You don't. You can keep A constant. Okay, so you can keep A constant. Then the issue is, for how long can you keep it constant? We have typically found, well, it depends on the flow conditions, you know, about 10 time steps. It depends on how rapid the transients are, but you are looking for the steady state solution. So in 3-dimensional flow, I am not really talking about 1-dimensional flow. You can try it out for 1-dimensional flow and see if it makes a difference. That you keep it constant for about 10 time steps, 15 time steps, that the savings are quite large. Okay, the savings are quite large. So you could keep A constant, remember that means A is not varying in time, A still varies in space. Okay, A is not varying in time, A held constant where this n is something that you determine. Is that fine? And very obviously this n may be small. If you now see now a little wrinkle on that, very obviously the n may be small when you are starting off, but as you get closer and closer to the solution, q is not changing much, so A is not changing much, right. So it can actually be kept constant for a longer and longer period, right, and as q converges, A will converge. Is that fine? Okay. So and remember, all of these can be done, whether you do LU approximate factorization, all of these can be done simultaneously. Okay. So I think, see, this is the deal, the argument started with just the simple idea, R goes to 0, I have my solution, and my objective is to drive R to 0. No, we are just using that one fact, right, and then trying to see what is what's the other degrees of freedom that we have. The minute I say, oh, this can be anything, see, that's a degree of freedom, then you can say, oh, it can be an optimal thing, then you can start hunting for optimals. Okay, is that fine? Okay, this is as far as I want to go with respect to obviously these arguments go on. If you want to do a transient dual time stepping and all, all of these arguments take place, go on to that. The only thing is, in dual time stepping case, the delta tau will change from point to point. Okay, so all of these arguments, whatever we have done here, will go on to that case also. Again, as I said, you could also do preconditioning the unsteady term, right. It doesn't, you can do local time stepping, there's a whole host, you can use a whole host of these tools, right, to make your code run faster, to get the solution. I won't say to make your code run faster, see, that's very strange, to get your solution back quickly. Okay, this is your objective, to get that solution back quickly. Is that fine? Okay, right. So what I want you to take from here is not just this, but that the process, the logic that I gave you. Okay, that's the important thing that I want you to get out of this, right, the process that I've gone through. Okay, that's the important thing. So I preserve the R, and then I don't really care about the others as much, and I use that to get my speed up. Fine. Okay. Now what I'll do is, I have talked about a whole bunch of mechanisms by which we can solve one dimensional flow. Let me suggest a test case for you. I'll just, in case when I did the demo, I didn't really point out the details of everything that I was running. Let me give you the specific details of what I was running so that you can try it out yourself. So the length of the pipe that I used, you can take it unit length if you want to start with, so it can be 1 meter to start with. Ask yourself the question whether the dimensions matter, under what circumstances do the dimensions matter. Okay, it's a critical question that, and to help you ask this question, I am going to pose an auxiliary problem, because we prescribed P naught and T naught there. Do you remember the conditions that I prescribed at the stagnation point? P naught was 101325 pascals, T naught is 300 Kelvin. You can start this off this way. Here of course we have 84,000 was what I had picked pascals, and to set the initial conditions, so I'm not going to write it here as a boundary condition. Remember the problem that we picked, the valve, we decided the valve was at the valve that's opened is at the inlet. So this condition, I gave it as 300 Kelvin, right. So the condition in here is whatever is here. So the initial condition, so this is initial condition, T equals 0, 300 Kelvin PA, and then you can decide how difficult or how easy a problem you want to start with. You can take U equals 0, indicating that the flow is stationary. So in fact when you open this suddenly, what you get is not, you will get a shock, and you have to apply for the to actually calculate the propagation speed, you have to use the Rankine-Huguenot condition that we were talking about the other day. You actually get a shock. Okay. So there are various things that you can do. You could set this, you can raise, I have taken a ratio of about 1.2, right. If you can keep the ratio at about that value and raise the whole datum up. So this could be at 1 atmosphere, this could be at 1.2 atmospheres. See what happens, right. This is at 300 Kelvin. Do you think it will make a difference if I change it to 500 Kelvin? Right. Is the problem more difficult to solve if it is at 1000 Kelvin? Ignore real gas effects. I am not telling you to take into account real gas effects. There are, once you start getting to 1000 Kelvin, your CP value changes, CV value, gamma changes, all of these things change. So we don't want to go there. You can still keep it at Euler equations, but the question is there a change there? Is it more difficult to solve? Is it easier to solve? Okay, because I have already pointed out, why did I pick this ratio of 1.2? Because this gives me an answer that is close to 0.5, Mach number 0.5. So this gives me an answer that's close to Mach number of the flow, it's close to 0.5, so that my eigenvalues are all in a nearby range. Okay, the problem is well behaved. So this is the other thing. So this process that I have gone through, to set up the problem is important. There is a reason why I am explaining this to you. So you may solve some other problem at a later date. You may be working on some research problem or an industrial problem. Somebody gives you something, you are doing the analysis, you want to develop code to work on that problem, you want to test your code while you are going through the developmental process. Pick an easy problem, pick a problem to which you know the solution, right. Pick a problem to which you know the solution, you anticipate the nature of the solution, what are the difficulties that are there. So you think about it a little, then say, okay, this is going to give me a problem, let me pick something that is near Mach 0.5. Okay, right. We could have done supersonic flow also, I could have done Mach 2. So you have to ask the question, why didn't he do Mach 2, why did he not do Mach 2, why did he do say Mach 0.5, okay, is that fine. So there are then you can fiddle around with these just to figure out how the code behaves and see what happens. Am I making sense? For various values of normally your experience, my suggestion, you may do this, everything is in dimensional form. Normally what you should do is you should non-dimensionalize the equation. Okay, so normally whether you do it now, whether you implement it this way and then later non-dimensionalize the equations is up to you. So use the non-dimensional form of the equations. Okay, in your fluid mechanics you would have studied non-dimensionalization and why you should look at the non-dimensional form of the equation. My suggestion is to look at the non-dimensional form of the equation, but we can come back here. You can ask yourself the question, if I take 1 meter or if I take 0.1 meters, does it make a difference? When does it make a difference? When is it the same, when is it different? Okay, we are dealing with Euler equations and that can create some element of confusion, fine. Once you have this is a relatively, see I have shown you all the features that you can get right in the demo, not much that you can get beyond that, right. You can get into trouble, you can try out various things, combinations that I have told you, and you can get into trouble. Really in gas dynamics this is not what we study, right. You do 1D equations, you set up the 1D equations, but the interesting stuff comes when you go to quasi 1D. 2 dimensions is tough, you go to quasi 1D or you go to 2 dimensions steady state, right. Okay, quasi 1D steady state. So I am going to draw I will draw half of it. Shall I draw the other half also? Something like that. This is a typical nozzle that you are used to dealing with. How did quasi 1D flow go? So you have some area variation. So the area variation, this could be the x direction. The area variation could be some s of x, s as a function of x, and the corresponding governing equations, the equations corresponding, governing equations corresponding to this would be, I will write it out, you can verify it, right, you can go back and check whether, so dou by dou t of q times s, just make sure I am using the same s, plus dou by dou x of E times s equals, now the right hand side is not 0, okay, simply because I have taken this s inside the brackets there, I get an extra term. On the right hand side I can place an h, the h is 0 p ds dx 0. You can do a simple sanity check right now. I would suggest that you make sure that you are able to remember what I told you earlier, right, make sure you are able to derive the equations. I may have made a mistake, but when someone is writing this you should be sitting there doing a simple sanity check. So when s is a constant, that goes to 0 and it can be factored out, you get back your 1D. So in that sense, yes, it is a superset, right, but as to whether the actual terms, individual terms are okay, right, is something that you have to look at. So this is not really that much of a change from your one-dimensional solver, right, it is really not that much of a change. But now interesting things can happen. The flow field is more interesting, right, now interesting things can happen, the flow field is much more interesting. So you could choose, again prescribe T0 and T0 here and prescribe a P ambient here and try out different things, try out different combinations, right, you could have subsonic, throat choked, throat not choked, right. So I would start with subsonic, throat not choked, that is where I would start, and then slowly build it up to where it is choked. Are you able to get the supersonic flow, right, are you able to get the supersonic branch? This is all for a small s, for a given s of x. Then you can try, if I change the s of x, right, fine. If you want to keep it simple, remember what I said, always try to keep it simple. So I wouldn't even do this first. What would you do first? I would just use I would just do a small converging duct, right, instead of a constant area duct I would actually do a small converging duct. So the s of x is known, s of x is simple, right, so s of x is a linearly decreasing function, s of x is known, prescribe the P0 and T0 here, prescribe P ambient here, in fact you can take the same values that are there, see what happens, okay, is that fine, right. You can then do, I would most probably do then a diverging section and then maybe a CD nozzle at that time, right, always good to go through a hierarchy of problems instead of jumping into the big problem directly, is that fine, okay. Are there any questions? Okay, I think this is, as I said, you have spent quite a bit of time in gas dynamics on quasi 1D flow, so I am not going to go through all the assumptions, right. You would expect that if S was varying very rapidly, you would expect that there would be issues, there should be problems, right. So because it is quasi one dimensional, the assumption is the area variations are not very rapid, right, otherwise the other 2-dimensional, 3-dimensional effects will come to play, okay. Fine. So I will now what I do is I go back to that equation, I am going to rewrite this, I am going to get back to accelerating convergence, and there is a whole class of schemes there is a whole class of schemes that we are going to look at. Okay, if I look at this, this looks like some matrix multiplying some vector equals the right hand side, it's the residue. Instead of using this to start with, I will start with Laplace's equation. Okay, I will start with Laplace's equation. So I am going to start with Laplace's equation as an example, and we will try to reason out. I am going to follow a certain path, but I want to recollect some of the things that I have done in the previous classes, the previous demos, more important, and conclusions that we have drawn in the demos, which I am going to use to rationalize or base, right, this acceleration scheme. Fine. So first think back to representing functions using hat functions, right. We tried representing sin x, sin n x, and we drew the following conclusions. So the conclusions were, there is a highest frequency that can be represented on a given grid. So there is a and remember, we are always talking about a uniform grid. For these discussions we are always talking about uniform grid. I do not want to even get to non-uniform grid right now. There is a highest frequency that can be represented on a given grid, right. What else? Is there anything else? So a variation of that, I turned the statement around. So whether a given wave number, highest frequency wave number, normally when they say frequency when they are talking about time, right, okay, wave number, okay, I turned it around for a given wave number, whether it is a high wave number or low wave number, high frequency or low frequency, depends on the grid on which you are representing it, taking the same thing, and right, which is also important for me. So whether a given wave number is high or low depends on the underlying grid. I want both these, right, though they are variations of each other, I want both of these. What else do we know? Now that I have defined what is high and low, we go to a different demo that we did. And we basically said that if you have these, if the scheme is dissipative in some sense, it seems to show that high frequencies decay faster than low frequencies. Fine. So certain schemes high wave numbers, I am saying frequencies again, I put the quote on high, so now I have told you what are high and low, that was the reason why I needed that. Okay, so high is with respect to the grid, low is with respect to the grid. So the grid is now going to become important, the underlying grid is very important. So if you say high wave numbers decay faster than low wave numbers, which means that by changing the grid, it is possible for me to change whether a frequency is high or low. That is the clue, okay, that is the clue. So we come up with this idea that we will use multiple grids. The scheme is called a multi-grid scheme. It is not a scheme to solve a problem, it is a scheme to accelerate a solution technique, okay, multi-grid scheme. The idea is to use multiple grids, right. So I will just take, if I think about one dimensional Laplace's equation, which is looks something like that. right, which you basically know on 3 grid points. I am not even going to bother to derive it, you already know. If these are p, p plus 1, p minus 1, then you know that given those two, right, you already know that up at iteration level n plus 1 or q plus 1 is the average of the adjacent points. So just a quick example as to how this happens. So if I have, if this is what I am plotting now is an error, okay, what I am plotting now is an error. If I have, so I want or if the end points are 0, then the solution should go to 0 either way, right. If I have my initial guess as something that is this way, we have seen this, I am only reproducing what we did in the demo, but I want to do it in a very specific fashion. So if you have a grid point at this trough, you have a grid point at this peak, you have a grid point at this trough, and if these correspond to p minus 1 and p plus 1, you can see looking at these three that the average will give me something that is going to go that way. That is basically what the averaging is going to do. Is that fine, everyone? So these 3 grid points are indeed effective in eliminating that little high frequency, and if you iterate once or twice, that high frequency will go away, and what you will be left with? The high frequency will go away, and what will you be left with? You will be left with the low frequency. Let us look at those 3 grid points again. That is p, p minus 1, p plus 1. And if you look at it, this and this, the average is very close. The changes that you are going to get with this grid are going to be very small, okay. On the other hand, if instead of that you had a grid point here, a grid point here, and a grid point there, now you can see that if you take the average, the change is much larger, right, or even make it even more coarser. If you had a grid point here, a grid point here, and a grid point there, you understand, the change is extremely drastic. But the tragedy is that though the change is drastic, the grid on which that you are able to do that is a very coarse grid, right. So somehow we have to come up with a mechanism by which we get the solution on the fine grid, but we use the coarse grids to eliminate the error, the low frequency error, the error that is low frequency on the fine grid. We want to use a coarse grid to eliminate it. The error which has low frequency on the fine grid, we want to use a coarse grid on which that error will be a high frequency. We want to use that coarse grid to eliminate that error. Is that fine? Okay, that is the motivation, that is what we are trying to do. This is called the multi-grid scheme. So we will see how we would do it, okay. So back here, Laplace's equation, we know if we were to discretize Laplace's equation, get a similar setup. I am not going to deal with this, right. So I know A is a flux Jacobian, but you humor me and allow A to be the coefficient matrix. So Laplace's equation, this is for Laplace's equation, this is not the flux Jacobian, right. A times phi of h equals f of h. I will put h there where h is the h represents the grid size. See, I already write the thing a little differently because I am saying that I am going to use multiple grids, I am aware that I am going to use multiple grids, right. So now I am being very careful, right up front I am going to be careful, I am going to say wait a minute, if I am going to use multiple grids I am liable to get confused, so let me stick H's up there so that I get the I can keep track of where I am, okay. Go back, if you go back to the part that we did Laplace's equation, you will see that we can actually write it this way. In 1D it would be, this would be a tridiagonal matrix, in 2D it is going to be a matrix whose bandwidth is much larger, okay. We have done this before, you can write it in this form, fine. The original equation is nabla squared phi equals 0, okay. If you get this exactly, then phi minus phi h will be a representation error, fine, right. So we solve this in some fashion, we can solve this in some fashion. You could guess a phi, you could guess a capital phi, right, you can guess a phi, a candidate solution for this, right. Am I making sense? Phi h is what you are seeking. If you have phi h, you have the representation, you have the answer, you have the value at the nodes, okay. You do not have this, you only have a representation of that on the computer. So if you have this, you have the solution. If you guess something which has an error in it, I will make it capital phi, you could guess that, okay. And in order to get to where I want to go, since I already know where I am headed, right, I am going to do this in steps. I am going to define an EH which is an error, which is the phi h which I seek minus capital phi h which I have guessed. Is that fine everyone? Okay, right. I will also define the residue RH as FH minus AH phi h. Is that fine? Okay. So what am I going to do? I am going to multiply this by, that by AH. So I get AH EH equals AH phi h minus AH phi h. I have not done any linearization and going from, really the original equations are linear, but it helps that the equation, the system of equations is linear, right. So I am using that fact here, it distributes over it, and this AH FH is okay. I have a small error here. For a minute I was staring at it saying wait a minute, there is something wrong. If I have the solution, the residue had to be 0, right. If I have the solution, the residue has to be 0. For a minute I was staring at it saying what's wrong, there is something wrong, okay fine. So what does this give me? This gives me FH minus that which is RH. So you get AH EH equals RH, okay. This equation incidentally is called the correction equation. This equation is called the correction equation. and in fact you can use this equation to solve the problem. Instead of the original equation, instead of this, you can actually use this to solve the problem. Am I making sense? How would you do that? You would guess a phi h, guess a capital phi h, compute RH, solve for EH, some iterative fashion, maybe you do not have to solve it, right, you do not have to use a direct method, but get an estimate for this. So find an EH from then update your pH new, and then you can iterate, you can do this iteratively. Am I making sense? So you could in theory you could use this equation. It is a little contrived, it looks a little contrived, right, but I just want to show it is equivalent to solving the original equation. Solving for this correction is equivalent to solving the original equation. Is that fine, everyone? Okay. Now we go one step further. So I can iterate, I can use either Gauss-Seidel or something of that sort. You can imagine that I do this, I find this, I do one sweep of Gauss-Seidel, I sweep through once with Gauss-Seidel, calculate the new one, go back here, find the new R, one sweep of Gauss-Seidel, and you keep on repeating that process. Okay, so you can set up an iterative scheme, right? You can use either Gauss-Jacobi iteration or Gauss-Seidel or something of that sort. You can set up an iterative scheme. Fine. So you are going through these iterations. You are going through these iterations. You do 10 iterations. It seems to be converging very nicely. All the high frequencies are gone, and now you are stuck with the low frequency terms, right? You have taken a 101 by 101 grid, and you are iterating away, right? And it is not going because the low frequency terms take a long time. So the question is, wouldn't it be nice if I could solve this problem now on a coarser grid, so that low frequency would turn out to be a high frequency on the new grid. Okay, so we do a small wrinkle. What we do is we take the same thing here, we take the same thing there, but we add a wrinkle. So we say we have the phi h, find the RH, okay, or let me write the, so iterate AH phi h equals FH few times. So to indicate that I am iterating it a few times, I will draw an arrow this way and say iterate, however many times you want to do it, okay, iterate it some n times. So you already have a disposable parameter, it could be 5 times, 10 times, you have to figure out what is good, right, iterate n times. Calculate RH equals FH minus AH phi h. So this is our current estimate after n iterations. What comes out of this is capital phi h, that is what comes out of that. Now in some fashion transfer RH to R2H. I do not want to call it R2H, so R2H. I have to, there is an extra step. Be careful with this part, I am going to come back and erase it and make some changes. Transfer from R to R2H, okay. RH to R2H, you understand what I mean? So if you say, wait a minute, how do I transfer? How does this magic occur? We will see it in one dimension. Right. So these are the grid points that I have, one dimension. I will keep it coarse so that we are able to, and let me get some colored chalk. So if I have a value here, I have a value at these points. So this is h, 2h would be this, okay. So to find the value here, to find the value at this point, to transfer, the simplest way to do is just throw that away. That is the simplest way to do it, just ignore these points, just throw those two away, take the one that is there, simplest way to do it. You do not like it, oh I slogged so much on all those adjacent points, should I really throw it away? This is what you feel regret, then do a little work, right. Take a weighted average, one of this, one of that, two of those, divide by 4, right, you understand what I am saying. So 2 phi p, phi p minus 1, phi p plus 1 by 4, right, and these are all capital Phis. Okay, this is phi, of course it should be r, I should actually be transferring r, right, it is not really phi, it should be r. Let me correct that, 2rp, rp minus 1, rp plus 1 by 4. All of these at h, this is, okay, so now you have a way by which you can get r at 2h. Am I making sense? At the point P, fine. Transfer from RH to R2H. Back here, iterate this n times, get a candidate phi, find the residue, transfer the residue. Okay, then what? On that coarse grid, solve A2H E2H equals R2H. When I say solve, I mean iterate a few times. Iterate a few times. Iterate to get E2H. Okay. Transfer E2H to EH. That shouldn't be difficult, isn't it? That shouldn't be, you can interpolate using the same example. If you want the value here, you can interpolate, right, you can interpolate, you can always get the value in between. Then repeat the correction, update, transfer it back, phi h new equals phi h plus EH that you have transferred. Okay. In fact, instead of, what you can do is, you can do this, and just to be sure that you have everything on the H grid fine, before you say I have the solution, you can iterate AH phi h equals FH a few more times, just to make sure you have a solution on that fine grid. Fine? Everybody, this is okay. You transferred to a coarse grid and transferred back. Now comes the little trick that we are going to do. Okay. Now comes the little gimmick that we are going to play. Come back here. You are here. You have done the transfer. Okay, you have done the transfer. Having done the transfer, come back here, and I am starting to iterate. Right? You are working on a 50 by 50 grid. You are doing iterations. You do 10 iterations, all the high frequency errors on that 50 by 50 grid disappear, but it still does not converge, because on that grid there are low frequency errors that grid cannot converge that rapidly. There are low frequency errors on that grid that do not go away. So you think, if only I could run them on a 25 by 25 grid, right, and you can. You can if you just change the notation a little, okay, so if you guys do not mind, we will go back here, change the notation a little, you change this to F2H, transfer RH, we will call it, change it to F2H. If you change it to F2H, what happens to this equation? That says AH E2H equals F2H. That looks very suspiciously like the original equation which we are trying to solve, which is AH phi H equals F2H, FH. Okay. So what you need to do is you iterate this another n times or m times or whatever it is, n1 times or n2 times whatever, to get this, and do not transfer it back. Instead calculate R2H. Now you understand why I wanted to call this F2H, because I propose to define a residue at this level. Calculate R2H, which is F2H minus A2H E2H. Transfer R2H to R4H. Okay, R4H. You could in theory transfer it to any size that you wanted, but it is a little easier if you keep them, if you keep the relationship transfer R2H to R4H. Iterate A4H E4H equals, oops, made a mistake, transfer R2H to F4H. Can't fall into the, now first time it is okay, second time we can't make that mistake. Now we know the game. R2H has to go to F4H. Iterate this. How many levels do we want to go? Well, that depends on where you started. If you started with 1023 grids or something, a huge number, huge size, 1000 by 1000 grids, right, and clearly there is some relationship to powers of 2, so you have to look at what is that relationship. Okay, I will let you figure that out. So then you can keep on having the grid, right, till you get to a point where you are happy with what you have, the convergence rate that you have. Fine, okay, oops, okay, that is fine. What I will do is we will get back to this. I will we will talk about maybe a little of this multigrid thing in the next class. Okay, fine, thank you.